Imagine building the most powerful computer anyone's ever dreamed up, something that could solve in minutes what would take our best supercomputers thousands of years. Now imagine that thing can barely stay switched on for a fraction of a second before it falls apart. Sounds made up. It isn't. That's basically been the joke at the center of quantum computing for decades. Quantum computers are supposed to change drug discovery, AI, encryption, you name it. They run on principles different enough from classical computers that they could, in theory, crack the encryption protecting global finance, simulate molecules atom by atom, solve optimization problems nothing else can touch. Huge potential. One brutal catch though. The second you try to actually use one, it falls apart. The quantum states that give these machines their power are so fragile that almost any interference from the outside world makes them decahere, lose their quantumness and crash. For years, the best these machines could do was hold a coherent state for microseconds, blink and the calculation's over. That's quantum decoherence, and it's been the wall the whole field has been stuck behind. Until now, apparently, labs around the world have spent the last few years chipping at this problem from different angles, and recently it's actually started giving. Coherence times are longer. Error rates have dropped below the threshold where practical quantum computing becomes possible instead of theoretical. The wall a lot of people genuinely doubted would ever come down has come down. But to see why that matters this much, you need to understand exactly what makes these machines so fragile to begin with. Classical computers, your phone, your laptop, even the biggest supercomputer on Earth run on bits. Each one's a 0 or a 1, on or off. Simple. Quantum computers work differently. They use qubits, and weirdly, a qubit can be 0, 1, or both at once. That's superposition. Picture it like this. A classical bit is a coin sitting on the table, heads or tails. A qubit is a coin still spinning in the air, both heads and tails, until you catch it and force it to land. Because a qubit holds multiple states at once, a quantum computer can check a huge number of possible answers simultaneously instead of one at a time, and the power grows exponentially with every qubit you add. Then there's entanglement, qubits getting linked in a way classical physics has no version of. Change one entangled qubit and its partner changes instantly, no matter the distance between them. Superposition plus entanglement is what gives quantum computers a shot at problems no classical machine could ever realistically solve. And here's the catch nobody's figured a way around, until apparently now. These properties are absurdly delicate. Think about balancing a pencil on its tip. A tiny vibration, a faint breath of air, and it tips over. Quantum states are worse than that. A stray photon, a vibration in the floor, a barely there shift in temperature, even electromagnetic noise leaking from some nearby device, any of it can make a qubit decahere. It drops out of superposition into a regular boring classical bit, and the moment that happens, whatever advantage you had is gone. Current quantum computers sit inside elaborate isolation chambers, cooled colder than outer space, shielded from electromagnetic noise, mounted on systems designed to kill vibration. And even with all that, coherence times have historically run from microseconds up to maybe milliseconds at best. A microsecond is a millionth of a second. That's roughly your window to run a calculation before everything crashes. It's a supercar with no top speed limit that turns itself off every few seconds. Amazing on paper, useless for an actual drive. You can't solve a hard problem if the machine keeps dying mid-calculation. That's been the reality of quantum computing since people started actually building these things. Huge promise on one side, equally brutal fragility on the other. Scientists have known about decoherence since the 1990s. What nobody knew was whether it could actually be solved, or whether quantum computing would just stay a gorgeous theory that never quite worked when you tried to build it for real. What changed wasn't a single light bulb moment. It was a pile of separate advances landing around the same time, in labs scattered across different countries, each one chewing through a different piece of the same problem. The breakthrough really comes down to two things happening together: a real leap in quantum error correction, and a parallel leap in the physical hardware underneath it. Start with error correction, because this is the part that sounds almost impossible until you see how they pulled it off. In classical computing, fixing errors is easy: copy the data, check it, fix whatever's wrong. Quantum computing has a problem baked into its foundation. Measuring a quantum state destroys it. It's the Schrodinger's cat thing: open the box to check, and you've already changed what's inside. So how do you catch and fix errors without measuring and therefore wrecking the exact information you're trying to protect? The answer turned out to be quantum error correction codes. Instead of putting one piece of information on a single qubit, you spread it across a bunch of qubits in a carefully designed pattern. The leading versions are called surface codes and topological codes. It's a little like writing one letter across a whole page using a complicated Patterns smudge a few characters and you can still figure out the original letter without ever directly reading it. These combined structures are called logical qubits, and each one's built out of dozens, sometimes hundreds, of physical qubits working together. The system checks for decoherence by comparing neighboring qubits and looking for things that don't line up, without ever collapsing the whole quantum state in the process. Spot an error. Fix it in real time. This had been theoretically possible for years, actually building it was brutal. Then the hardware caught up. Engineers came up with qubit designs that isolate much better from environmental noise. IBM's Transmon qubits now hold coherence past 100 microseconds, a real jump, and finally enough time for error correction algorithms to actually do something useful. Cryogenic systems got better at holding temperatures. Within thousandths of a degree of absolute zero, shielding improved, cleaner materials cut down on internal noise. But here's the bit that actually made headlines. Google's quantum AI team showed something nobody had pulled off before: add more qubits dedicated to error correction, and the error rate goes down instead of up. Sounds like it should be obvious. It really isn't. Before this, throwing more qubits at the problem usually made things messier. More complexity, more errors than the correction could keep up with. The system got worse, not better. That's exactly what had stalled everyone for so long. Google flipped that. More qubits, better correction, longer coherence, calculations that actually finish instead of collapsing halfway. Researchers call the point where this flips the break-even point, and the system had genuinely crossed it. Other labs followed fast. Groups at Yale, MIT, the University of Sydney published results with error rates dropping below the critical threshold. IBM announced logical qubits stable enough to run thousands of operations before failing up from dozens before. What actually matters here is that they've pushed past what's called the fault-tolerant threshold. That's the math point where you're fixing errors faster than they pile up. Below it, decoherence wins, every single time, eventually. Above it, you can scale almost indefinitely bigger machines, longer coherence, more complex calculations that don't fall apart halfway through. For the first time, quantum computers aren't just sitting there proving quantum physics works in a lab. They're starting to actually finish what they start, and crossing that line doesn't just make these machines marginally better, it changes what they're useful for, and which industries are about to feel it. Solving decoherence isn't only a win for physicists. It's the point where quantum computing stops being a curiosity in a lab and starts being a tool that reshapes entire industries. Take drug discovery first. A single new medicine right now takes over a decade and costs billions to develop. The reason's complexity: molecules interact in ways so tangled that even the best classical supercomputers can only approximate what's actually happening. Quantum computers can simulate molecular interactions atom by atom accurately, because they run on the same quantum rules molecules themselves obey. Researchers think this could compress drug development from years down to months, finding treatments for Alzheimer's, cancer, drug-resistant infections faster than anything possible today. Materials science is facing something similar. The quantum behavior of electrons decides almost everything about how a material conducts electricity, stores energy, absorbs light. Simulating that accurately needs quantum computation. With fault-tolerant machines, scientists could design room temperature superconductors that lose zero power in transmission, battery materials that charge in minutes and last 4 days, carbon capture compounds built atom by atom for the job. Then there's cryptography. Most of the encryption guarding global banking, military communication, personal data relies on math problems classical computers can't crack in any reasonable amount of time. Quantum computers could crack them. Governments and major institutions are already racing to build quantum-resistant encryption before that window closes on them. Financial institutions are dumping money into quantum optimization for risk modeling at a scale that isn't possible right now. AI researchers think quantum hardware could speed up machine learning enough to turn years of training in 2 days. None of this is a distant maybe anymore. Pharma, finance, tech companies across all of it are spending billions getting ready for a world where this actually works. Honestly though, the real story's bigger than any single use case here. This is a fundamental shift in what computers are even capable of, and that comes loaded with its own set of new problems. Crossing the fault-tolerant threshold is genuinely a big deal, but it's worth being honest about what it does and doesn't mean, because the gap between where things stand right now and where quantum computing actually needs to get is still pretty wide. What this breakthrough unlocks most immediately is scaling. Up until now, adding more qubits to a quantum computer usually made things worse. More qubits meant more chances to decohere, more noise, more errors piling up faster than they could get fixed. The system was fighting itself. Now that error correction actually works the way it's supposed to, Adding qubits makes the system stronger instead of more fragile. The ceiling's lifted. Engineers can start building toward the millions of stable logical qubits the biggest applications actually need. Building 1 million stable qubits, though, is a genuinely massive engineering problem. Today's best quantum processors run hundreds to a few thousand physical qubits. Getting 2 millions while holding on to the precision and isolation these recent breakthroughs showed off needs manufacturing advances that flat out don't exist yet. Every qubit has to be made with extraordinary consistency. The cryogenic systems holding temperatures colder than deep space have to scale up without losing performance. The electronics managing thousands of qubits at once have to get faster, more precise, way more efficient. There's a software side too. Quantum hardware's moving fast, but quantum algorithms, the actual instructions telling these machines what to do, are still pretty early. We know quantum computers are good at specific things: simulating quantum systems, optimizing tricky variables, breaking certain encryption. The full map of what they can and can't beat classical machines at is still getting drawn. Building software that actually exploits the hardware is going to eat years. Then there's geopolitics, and this is maybe where things feel most real. Quantum computing isn't a science project anymore. It's a strategic technology with real weight behind national security, economic competitiveness, global power. The US government's put billions into quantum research through the Department of Energy, the National Science Foundation, DARPA. China's gone harder building dedicated quantum research cities, publishing a volume of quantum research that now rivals the entire Western world combined. The EU launched a €1 billion quantum flagship program. Everyone involved understands that whoever gets too large-scale, fault-tolerant quantum computing first walks away with a serious edge. The most immediate security worry is cryptography. Current encryption protects military communication, intelligence networks, financial systems, critical infrastructure. A powerful enough quantum computer could break widely used encryption in hours, not years. Intelligence agencies already operate on the assumption that rivals are hoovering up encrypted data right now, planning to crack it open later once the hardware's there. It's called harvest now, decrypt later, and it means the push toward quantum-resistant encryption is already urgent no matter exactly when practical quantum computers actually show up. Different countries and companies are betting on different hardware approaches, and that spread actually matters. Superconducting qubits, Google and IBM's approach, run fast but need extreme cooling. Trapped I-don't systems, the bet companies like IonQ and Quantinum are making, hold coherence longer naturally but run slower, photonic. Quantum computers use light particles as qubits and work at room temperature, but they've got their own scaling headaches. Microsoft's betting on topological qubits, a genuinely different approach that could mean inherently lower error rates if it can be made to work reliably. Every path has real strengths and real weaknesses, and honestly, the competition between them is a good thing. Nobody actually knows yet which one gets there first. What does seem fairly clear is that hybrid systems, machines mixing classical and quantum processors working side by side, will almost certainly be the first practical quantum tools that actually ship commercially. Classical hardware keeps doing what it's already good at. Quantum processors handle the specific calculations where they have a genuine edge. Big tech companies are already building toward this, and it might end up being the realistic bridge between today's lab demos and tomorrow's actual products. The decoherence breakthrough doesn't hand us any of this overnight, but it knocks out the basic barrier that made all of it questionable in the first place. The questions move from whether quantum computing will ever work to how fast the remaining engineering gets solved. So where does that leave things? For the first time, nobody serious is asking if quantum computing works. The question is what we actually do once it does. We started with a paradox: the most powerful computers ever dreamed up, machines that could solve in minutes what would take classical supercomputers longer than the age of the universe, and yet they could barely stay running for a fraction of a second. They kept collapsing under their own fragility before they ever got the chance to show what they could really do. For decades, that was quantum computing, basically enormous promise sitting right next to crushing limitation. That paradox is mostly resolved now. By getting past the fault-tolerant threshold, by building error correction that fixes quantum states faster than decoherence breaks them, scientists haven't just nudged quantum computers forward a bit. They've proven the entire idea holds up. They've shown the principles quantum computing runs on can actually survive contact with a messy, noisy, real world. That's more than a technical milestone. History's worth a quick look here. Big technologies almost never show up fully formed. They sit around for years, sometimes decades, stuck behind one stubborn barrier that makes everything past it impossible. The transistor was understood as an idea well before manufacturing got precise enough to actually build one reliably. The internet existed as a network for years before the protocols and infrastructure existed to make it something ordinary people could use. CRISPR was understood in theory long before anyone figured out how to apply it accurately inside a living cell. Each time getting past that one wall didn't just unlock the technology, it set off a sprint. Progress that had crawled for years suddenly moved fast enough to catch even the people working on it off guard. Quantum computing looks like it's hitting that same kind of moment right now. The conversation has genuinely shifted. Researchers aren't debating anymore whether quantum computers can hold coherence long enough to matter. They're arguing about timelines, applications, which architecture wins, they're building, they're scaling, they're writing algorithms for hardware that'll exist in years, not decades. The question went from whether this works at all to what we actually do with it now that it does. The wall's down. Machines that used to collapse in microseconds are stable enough now to compute, fix their own errors, and scale up. Industries that were preparing cautiously are preparing urgently. Governments that were watching from a distance are pouring in real money. Scientists who spent careers fighting the fragility problem are turning to whatever's next. The quantum future's been promised for decades. What's different now is that it's actually getting built, and whatever comes out of the next 10 years might end up changing more than most of us are ready for.